Okay, we should be live. I'll test my audio and everything. We usually have more videos than subscribers. So go click that subscribe button. Will be helping the project. But mainly I'm after feedback on the website. So go check the website out. We'll be going over as a new look. You can now scroll through different sections. It's a bit like a book, obviously self-published, but still original work. Well, mostly we are using ChatGPT, but one of those employees that don't do much unless you keep poking them. So go over the website. If you have preferences of me focusing on a specific tool, do let me know. And some of them needs to be optimized for mobile, stuff like that. Yeah, if the robot can do it. I mean, the robot did all this new hovering, what's called sticky label. I forget what it's called. Doesn't matter. Check. A navigation bar. Yeah, with like the burger and everything. And it's disappearing when you scroll down and appearing again when you scroll up. So it's kind of nice. So we have ethics and AI, brain AG, cardio and ECG, simulations and games. So there's a lot of interesting stuff there that should be of interest to general public as well. Have some stuff on imaging. We'll be touching on this brain 3D in a sec. Devices, yeah, that needs more work. We have some 2 broken pages in the moment. The one on imaging is actually working. That's what it looks like at the moment. Not the volumetric data is loading for some time. Is it loading at all? Yeah, it might be loading forever. To refresh the pages. Yeah, how many resources? 200 megabytes just in that tab alone. And still loading, loading, loading. Yes, that's for the volumetric data. It's still loading. This is crazy. Yeah, definitely have to reduce the loading time. I mean, right. And it finished in a whopping 52 seconds. It was loading the volumetric data. Yeah, that's not ideal, is it? That might be a bit of a problem there. I mean, the tool is already live. You can check it out yourself. Probably won't be publishing the link because it will be overloading my server, essentially downloading that data from it. Question for me, the question is if a CDN can be used, if it's actually being fetched. I'm not entirely sure. So we have obviously the code for it. The data is in a static folder. Why do we have a data copy? That shouldn't be there. Yes, we have a JSON file. You can't see that. So we have a JSON file for the volumetric data, and then we have the images for each slice. There are 100 of them. Uh, 100 slices in each direction. So sagittal, coronal, and axial. Oops. There's something weird. There is something. Okay, they're not in order, and there are a gazillion of them. 255. No, they are in order. 100, but they are more than 100. I think it's expecting only 100. I have to check the code. Yeah, I did notice there was something. Yeah, because it's jumping. Which one is that? Requests. Where are requests? They're here. Why is it actually not being shown? Console sources. And why is it not in a static folder? We have static. That's a bit unusual. Well, yeah, a couple of issues. First, it's loading forever. Yeah, now my CPU calmed down a bit and then starting throttling again, and that's not good. Yeah, I don't quite get why is it not in a static folder, because it matters for the CDN, for the content delivery network, for the actual data, because I guess images can be cached, so for them to actually being delivered by the, well, in my case, Cloudflare, that would be quite handy, wouldn't it? Again. Yeah, I'm having an issue of the CPU, and all the fans are being just in front of me, and they're probably going into the microphone when when the filter, the noise suppression is off, yep, there will be a lot of noise. And if we stop this for a sec, no, there's still a lot of noise. No, it's like 20 dB or so less. Yeah, this will be a heavy tool. I'm thinking, yeah, we need to minimize it somehow. And now it's actually loading much quicker, so it's been in the memory for the browser. And I'll get about minus 35 dB noise when the fans are on. When you turn it off, does it go down? Yeah, about minus 50 or so. So about 20 dB coming from essentially my server is in front of me. So yes, I can suppress the noise. Now it should go much quieter. Yes, when I'm not talking, going all the way minus 60, so essentially no noise whatsoever, which is good. But the problem with this is it's not perfect. When you actually talking, the noise will be still audible. So that's yeah, need to sort it out. So a bunch of things. But yeah, this tool. Yeah, whopping 50 seconds to load. We are generating the metadata ourselves. So we have this pre-processing file, a Python script. Yeah, we're using this. Yeah, we need to mention the source. We have another file that's just doing inspection. Inspection of the Nifty file. Can we run that quickly? Yeah, we get all this weird stuff from it. Okay, this is the kind of stuff ChatGPT should be able to pass and tell you what it is, maybe. we have this info file that tells us what the structure of the project is, but we can definitely get rid of that copy. We need to update the file and folder structure. See if should be a job for GitHub Copilot. We need the workspace handle. Let's see if it can do it. I don't know if it's only looking at files that are currently open or all the files in the folder. It's searching references, pre-processed copy info text. No, we don't have the data copy anymore. Well, I mean, we can delete it manually, but we want the robot to actually know what are, we need like a text version. This is not the best way of doing it, is it? We should be getting it from the terminal. Terminal. How do we get the folder and the file structure for a certain Visual Studio Code project? So we have a certain folder, and we want to list all the files and subfolders in text format using Ubuntu terminal. Well, it should be the same terminal that we have. Do we have 3? Yeah, we heard about this before. Right. Then folder structure bash tree. We can have it here. Run tree command to list all the files and subfolders. This is in terminal, obviously. Okay, so maybe we don't need to expand. Yeah, tree project structure. So we'll have project structure text. Yeah, this would be a long thing. You can't actually minimize sections, can you? And we can exclude PNG. Okay, this is really good. And it will be updated as well. The project structure, 10 directories, 19 files. Okay, JS. Yeah, we don't actually need these libraries. Yeah, not including any PNG files. Okay, so we have this project structure. But we have copies of stuff. Let's actually check that if we remove this pre-process and go run that command again, so including all the files without PNG files. And yeah, that's gone. So that's good. I actually think we need start another GPT. Yes, we have this structure, right? This HTML should have a prompt a file as well. So we're working with this nifty file. That is only 30 megabytes. So if it's 30 megabytes, how is it? That when the page is loading, it's like 300 megabytes or so. That's not good, is it? Oops. Keep forgetting. It's Control Shift C. Yes, so we are loading this file. So we are loading this file that is only 30 megabyte large or small, but then the page loads about 300, 500 megabytes. It's crazy. There's no errors or anything. Yeah, this page, because also in the image provided you can see how the page looks like. This tab for the browser is a whopping 523 megabytes. The original nifty file is only is only is only 31 megabytes. So what can we do? What can we do? To make the web application better, there's also another question, is how the slices are being loaded. It seemed not to be loading more than 100 slices, even though there should be more. If you can look at the file and folder structure, there are 253 PNG files in coronal folder, and similar amount in sagittal and the axial folders. Now question is, there are two questions. First, why is it only loading? Can we make sure it's loading them all, not just the first 100? Second question is, how do we make sure all this is being loaded in the CDN? So how do we make sure it's being cached? by the content delivery network, in my case, Cloudflare. Let's try a single shot prompt. Yeah, we need a main.js. Did we load it already? No. Yeah, we need to give it the main.js is important. But in the meantime, I can actually read this one.
Issue 1, limited loading of slices. The issue you're facing, where only the first 100 slices are being loaded, may be due to how the slices are being read and processed in your JavaScript code. Here's what you should do to address this. 1. Review slice loading logic. Ensure that your main.js or any other relevant JavaScript file is correctly iterating over all the slice files in the folders, axial, coronal, sagittal. It's possible that a loop or file reading mechanism is prematurely stopping or limiting the number of slices being loaded. If the files are being fetched via HTTP requests, make sure there's no limit set in the request loop. If the files are being preloaded into an array, confirm that the array is large enough to hold all the slices. Verify that the file names follow a consistent naming convention and that no slices are being skipped due to naming mismatches. Number 2, check browser limits. Browsers may impose limits on the number of concurrent network requests or the amount of memory that can be used. Ensure that the browser isn't throttling your requests. You might need to implement a more efficient loading strategy, such as lazy loading or batching the slices. Issue 2, high memory usage. The high memory usage might be due to large, uncompressed image data being held in memory. You can try the following. 1. Image compression. Compress the images before loading them. Use formats like WebP that offer better compression for web use. 2. Lazy loading. Implement lazy loading so that only the slices that are currently in view are loaded into memory. This will significantly reduce the initial memory footprint. 3. Efficient rendering. Ensure that you're disposing of any WebGL or 3JS objects that are no longer in use to free up memory. Issue 3, caching with Cloudflare. To ensure that all assets, images, JavaScript files, etc. are cached by Cloudflare, you need to configure both your server and Cloudflare settings correctly. 1. Set cache control headers. In your Apache configuration or within Flask, set appropriate cache control headers for your static files. This could look something like this. Python from Flask, import send from directory, make response at app.route/static/path file name. And def static files file name, response equals make response send from directory static file name. Response.headers cache control equals public, max age 315v360,000. Cache for 1 year, return response. This ensures that the files are cached for a long time. 2. Cloudflare cache rules. Log into your Cloudflare dashboard, navigate to the caching section, and set up cache rules for the /static/ directory. You might want to set a cache everything rule for these paths. 3. Minification and compression. Enable Cloudflare's automatic minification and compression options to reduce the size of your JavaScript and CSS files. 4. Check caching. Use browser developer tools or online tools to verify that the files are being served from Cloudflare's cache rather than directly from your server. By addressing the slice loading logic, optimizing memory usage, and ensuring proper caching, you should be able to improve both the performance and scalability of your web application. Your code is setting up a 3D brain MRI viewer using 3JS and managing 3 different 2D slice views for axial, sagittal, and coronal orientations. There are a few optimizations and corrections that you can make to ensure better performance and functionality. 1. Optimizing memory usage and slice loading. One issue you mentioned earlier is the high memory usage when loading a large number of slices. To address this, downsample factor. You have a downsample factor set to 1. If you experience performance issues, consider increasing this factor to reduce the number of points in the 3D visualization. Efficient memory management. Ensure that when a new slice is loaded, the previous slice is dereferenced to allow garbage collection. This prevents the browser from holding on to unnecessary memory. 2. Caching static assets with CDN Cloudflare. Since you're using a CDN like Cloudflare, ensure the slices and other static assets are properly cached. Cache control headers. As mentioned earlier, use cache control headers in your Flask app or Apache server configuration to ensure that static files like slices and JavaScript files are cached. Example, a pactual if a mod expires.c expires active on expires by type image PNG access plus 1 year. Expires by type application JavaScript access plus 1 year if module. Cloudflare settings. Ensure Cloudflare's caching settings are set to cache these files effectively. In Cloudflare's dashboard, set a page rule to cache everything under /static or your slices path. 3. Handling large volumetric data. The large data size might be leading to slower performance or incomplete rendering. Consider the following. Progressive loading. You might want to implement progressive loading of slices where you load lower resolution slices first, then progressively load higher resolution ones. Web workers. Consider offloading the processing of volumetric data to web workers to avoid blocking the main thread. Number 4. Ensure consistent slice navigation. You're using a modulo operation to loop the slices with the %100 operation. This assumes you have exactly 100 slices, which might not be the case. Adjust this to use the actual number of slices. JavaScript function update axial view increment. Current axial index equals current axial index plus increment plus total axial slices. Sent total axial slices. Fetch and draw slice axial, current axial index, axial context. Function update sagittal view increment. Current sagittal index plus increment total sagittal slices sent total sagittal slices. Fetch and draw slice sagittal, current sagittal index, sagittal context. Function update coronal view increment. Current coronal index equals current coronal index plus increment total coronal slices sent total coronal slices. Fetch and draw slice coronal. Current coronal index, coronal context. You should set total axial slices, total sagittal slices, and total coronal slices dynamically based on the number of slices available in each folder. Number 5. Dynamic base URL handling. You correctly handle the base URL based on whether the application is running locally or not. However, you should ensure all your assets are accessed relative to base URL to avoid issues when deploying to different environments. Number 6. Responsive renderer resize. Your resize renderer to display size function resizes the renderer when the window size changes. Ensure this is correctly updating the camera's aspect ratio. JavaScript function resize renderer to display size renderer. Const canvas equals renderer.dom element. Const width equals canvas.client width. Const height equals canvas.client height. Const need resize equals canvas.width equals width. Canvas.height equals height. If need resize, renderer.set size width height false. Camera aspect equals width/height. Camera.update projection matrix. This ensures that the rendering adjusts to different screen sizes smoothly. Task 7. Error handling improvements. You're catching errors in the fetch for volumetric data, but not in the image loading. Consider adding a more comprehensive error handling strategy for images. Based on the Cloudflare cache settings shown in the image, here are some recommendations for optimizing your cache configuration. 1. Purge cache. Custom purge. Use this option if you only need to clear specific files, like when updating a particular asset, e.g. main.js. This helps maintain overall cache efficiency while ensuring users get the latest versions of critical files. Purge everything. This option should be used sparingly, as it forces Cloudflare to fetch everything anew from your origin server. It's useful if you've made significant changes to your site that affect multiple files. 2. Caching level. Standard. The current setting caches static content while considering query strings. This is generally a good balance for most websites, especially if you have URLs with query strings that should return different content based on those strings. Recommendation. Keep this setting as is unless you have a specific reason to change it. If your site does not use query strings for varying content, you could consider switching to no query string to increase cache hits. 3. Browser cache TTL, 5 minutes. This setting means that a visitor's browser will cache files for 5 minutes before checking with Cloudflare if new content is available. Recommendation: for static assets that don't change often, like images, CSS, JS files, you might want to increase this TTL to something longer, e.g., 1 day, 1 week. This reduces the number of requests to Cloudflare and improves load times for repeat visitors. For dynamic content, if you have content that changes frequently and needs to be updated often, a shorter TTL makes sense. You can also set different TTLs for different types of content via page rules in Cloudflare. Additional recommendations: enable automatic cache purge. Consider using Cloudflare's API or integration with your deployment process to automatically purge specific files or paths when you deploy updates to your website. Leverage cache control headers. Set cache control headers in your server configuration, Apache Flask, to work alongside Cloudflare's caching, giving you more granular control over what gets cached and for how long. These adjustments should help optimize the performance of your web application by balancing the need for up-to-date content with the benefits of caching.
Okay, can you explain how is it that the data file that we have is only 32 megabytes? But the volumetric data JSON file is 98 megabytes. It's not compressed. Yeah, we have a bunch of these files. Yeah, I have to make sure we are using the same one. Yeah, we're using the subject 0 session 1 T1W. Yep, that's the one. And it's not compressed.
The discrepancy between the original NIFTI file size, 32 megabytes, and the volumetric JSON file size, 98 megabytes, likely stems from several factors related to how the data is represented and stored. 1. Data compression in NIFTI. NIFTI compression. NIFTI files, especially when stored as .nii.gz, are typically compressed using gzip. Compression algorithms reduce the file size by efficiently encoding the data, particularly if there are repetitive or zero values, which are common in medical imaging data. This compression can significantly reduce the size of the file on disk. JSON format. JSON files are not compressed and store data in a plain text format, which is much less efficient in terms of storage compared to binary formats like NIFT. Every number in the volumetric data, along with structural information such as brackets and commas, adds to the file size. Data structure and overhead in verbose representation. JSON stores data in a human-readable format, which includes a lot of overhead. Each data point, voxel value, in the volumetric data is represented as a string of characters. This is far less space-efficient compared to binary formats, where data might be stored as 16-bit or 32-bit integers or floating point numbers. Redundancy in data. In a volumetric JSON file, each voxel in a 3D grid is likely represented with explicit coordinates or array positions, and possibly with additional metadata. This explicit representation increases the file size significantly. 3. Data resolution and sampling. Voxel data. If the JSON file represents the voxel data at a high resolution, e.g., each voxel is represented individually rather than downsampled or aggregated, this can lead to a large increase in file size. Each voxel's intensity value must be explicitly stored. Additional data. The JSON file might also include additional information such as color mappings, material properties, or other metadata that isn't present in the raw Nifty file, contributing further to its size. 4. Potential duplications. Repeated data. The JSON file might contain repeated or redundant information, such as multiple instances of the same data structure, which isn't necessary in the compact binary format of Nifty. Example breakdown. Nifty file stores voxel intensity values as compressed binary data, optimized for size. JSON file represents each voxel with additional structural data, potentially storing data in an uncompressed verbose format, which leads to a much larger file size. How to handle this? To reduce the size of the JSON file, consider the following strategies. Compression. Compress the JSON file, e.g., using gzip before serving it. This can dramatically reduce the size, similar to how Nifty files are compressed. Downsampling. Reduce the resolution of the data represented in the JSON file, which reduces the number of voxels that need to be stored. Binary formats. Instead of using JSON, consider using a more space-efficient binary format to store volumetric data. For example, using a format like .bin, or converting the JSON back to a compressed binary format can save space. By understanding the factors contributing to the file size, you can make more informed decisions about how to store and serve your volumetric data.
So is it possible to serve the original Nifty file without pre-processing it in Python? I'm thinking starting another web application and compare the performance of the two. If you can elaborate in text alone, continuous sentences, full paragraphs, without code. That would be great. Because I'm pretty sure I tried it. Didn't really work. It's probably worth trying again.
Yes, it is possible to serve the original Nifty file directly to the web application without pre-processing it into a JSON format. This approach would involve leveraging client-side processing to handle the Nifty file and visualize the volumetric data in the browser, potentially offering several advantages in terms of performance and efficiency. Serving the original Nifty file. To serve the Nifty file directly, you would need to transfer the raw.na.gz file from your server to the client. This can be done through a simple file download mechanism, where the NFT file is fetched via a standard HTTP request. Once the file is on the client side, JavaScript or WebAssembly for more performance-critical applications could be used to process and render the Nifty data within the browser. Client-side processing of NIFTY files. JavaScript libraries like nifty.js or papaya.js can be utilized to read and process Nifty files directly in the browser. These libraries can decompress and parse the Nifty format, allowing you to extract the voxel data needed for visualization. Once the data is parsed, it can be passed to Three.js or other WebGL-based frameworks to render the 3D volumes or slice views. Benefits of serving Nifty files directly. 1. Reduced server load. By offloading the pre-processing and volumetric data conversion to the client, the server's computational load is reduced. This could be particularly beneficial if multiple users are accessing the application simultaneously. 2. Lower bandwidth usage. The original Nifty file, even in its compressed .nii.gz form, is typically smaller than a fully expanded JSON file representing the same data. Transmitting the compressed file reduces the amount of data transferred over the network, potentially speeding up load times and reducing bandwidth costs. 3. Flexibility and real-time interaction. With the data being processed on the client side, you can potentially offer more interactive features, such as real-time adjustments to the visualization, e.g., applying filters, modifying thresholds, or changing visualization parameters, without requiring round trips to the server. 4. Comparison of performance. By building another web application that serves the raw Nifty file and processes it client-side, you could directly compare this approach with your current method that pre-processes the data into JSON. This comparison would give you insights into which method is more efficient in terms of load times, memory usage, and overall responsiveness of the application. Challenges and considerations. 1. Client-side performance. While offloading the processing to the client can reduce server load, it might increase the computational burden on the user's device. Users with lower-end hardware might experience slower performance when handling large Nifty files, especially if the visualization requires significant processing power. 2. Browser compatibility. Ensure that the client-side libraries you use for processing Nifty files are well supported across the browsers your users might be using. WebAssembly can help optimize performance, but may have varying levels of support depending on the browser and platform. 3. Security concerns. Serving raw medical data files like Nifty directly to clients requires careful consideration of privacy and security. Ensure that any sensitive data is adequately protected and that your application complies with relevant data protection regulations, e.g., GDPR or HIPAA. 4. User experience. The user experience might differ between the two methods. Direct processing in the browser could introduce longer initial load times, depending on the size of the Nifty file and the efficiency of the client-side processing. Balancing the initial load time with the application's interactivity and responsiveness will be key. Next steps. You can proceed by setting up a separate web application that focuses on serving the raw Nifty files and processing them client-side. By doing so, you can directly compare the two approaches. Pre-processed JSON versus raw Nifty. Analyze the differences in load times, memory usage, and responsiveness between the two methods. User experience feedback. Gather feedback from users or testers to determine which approach offers a better experience, considering factors like interactivity, ease of use, and performance on different devices. By conducting this comparison, you'll be able to make an informed decision on whether to continue pre-processing the data server side or shift to a more client-driven approach. This could lead to significant improvements in your application's performance, scalability, and user satisfaction.
Okay, in a quick response, how difficult would it be to generate a code that will just take, by the way, should it taking the nifty uncompressed or compressed file? If you can elaborate more on how complicated the code would be and how many resources does it require by the user to have for it to actually run properly, and also touch on if it's possible to actually store the nifty file in the CDN. Quick response, no code. Yeah, because currently we have this thing that is pre-processing everything on the server and then serving a JSON file for this volumetric data and the images. There's one problem. Might as well run it locally as well. And the idea is we'll start another application that just serves the nifty file to the front end and then doing mainly JavaScript processing for everything else. If you haven't checked this site yet, please go do so. Yeah, we'll be testing locally. Yeah, so we get this get responses over here. That we want to try and avoid in the next application. Yeah, so as you can see, once it actually loading the whole thing, is not requesting anymore because it's being stored in the browser. Ooh, 1.5 gigabyte stored in the browser. Okay. Yeah, so that's not cool. And then it will forget about it. Yeah, so you saw it's like it started sending more GET requests. Yeah, so if you leave it, if you don't touch it for like 10 seconds or so, it then starts loading them from the server again. So that's not ideal. Yeah, not anymore, not yet, but yeah, this one is being loaded already. Yeah, note that the JSON file for the volumetric data is only just under 100 megabyte, but the original Nifty file is only 30 megabytes. And now with the images and everything, I have 1.5 gigabytes loaded in the memory of the browser. So that's not cool. And it's using the GPU. Yeah, and there's a lot of Chrome going around. Well, I do use it for other things as well, but yeah, now it's loading from the server again. I don't know why. Why does that happen? We had some advice there on changing the caching level. No, it's actually suggesting keeping it as is. Yeah, but when we run it locally, it's actually nothing to do with the CDN. Yeah, we have some advice on... We'll potentially have another application, so we'll have the Brain 3D, and then we'll have Brain 3D JavaScript version. So this one is relying on the server essentially too much. It's fetching stuff off the server. It's already available, it's published, but we wanna improve on it quite a bit. And for whatever reason, it's only looking at the 100 slices instead of about 250 something. So apparently in our JavaScript, yeah, we have a 100 set in here. Yeah, we use Copilot for this with a workspace handle. Is the code only loading the first 100 images instead of loading the whole stack? There should be about 250 something in each folder, in each direction. Yes, currently through the first 100 images, yeah, I can turn it into 250. Hey, can we check the exact number of images automatically, programmatically, instead of hard coding it? Fetch image count. And we have it set to 50. We'll probably set it to like 100 by default. So we have fetch image count in each orientation. Okay, that's kind of important, so we're doing it programmatically. A question, so when Copilot is generating stuff, it has this big apply in editor. So I suspect we have to select the whole code, hit the apply button. We currently have 182 lines of code. And here we should end up with about 200 or so. It's still applying changes. And no, it reduced it to 164. That doesn't make much sense. We're happy to test, but it's giving me all these errors. So it stuffed something up. So yeah, integration of code is a bit of a pain. With GitHub Copilot, how do you integrate properly? Oh, Yeah, I want to change the default to like 100, so it's like in the middle of the slice. We want to do many other things as well. We want to actually, whenever we showing slices, we want to actually see where they are in the volumetric data. The problem is this tool is already quite heavy. We probably don't want to add too much to it. Or shall we? This is not in production yet, so we... Okay, so we have this JavaScript. We would like to do a couple of things. First of all, we would like to programmatically check how many slices we have. So how many images we have in each direction, axial, sagittal, and coronal. So we can actually flick through, cycle through all of them instead of just the first 100. Also, another change is that we want the current axial, sagittal, and coronal index to be 100. So we want to show roughly the mid slice, the middle slice. Let's see. Yeah, because like GitHub Copilot is nice, but I don't know how to integrate this thing, so it becomes kind of useless. What if we just stay in, say, line, pass the code and then tell it to apply changes? We're expecting more lines of code, so it should be, we expect about 200. Okay, so you apply them at the end. That's not cool. That's not cool because we need to refactor the whole thing. Can you update and regenerate the whole code with all the necessary script? And this one is not coding anymore. Well, yeah, before I did ask it to just generate text, so I might read it.
To achieve the goals you've outlined, here's how you can proceed conceptually. Hacksner 1. Programmatically, determine the number of slices. You want to dynamically determine the number of slices, images, available in each orientation, axial, sagittal, and coronal, so that the JavaScript code can cycle through all available slices rather than being limited to just 100. This will involve fetching the number of slices. You need to update your backend, e.g., Flask or another server-side framework, to return the number of available slices for each orientation when the application is initialized or when needed. Storing slice counts. The slice counts should be stored in JavaScript variables so they can be used to determine the boundaries when cycling through the slices. 2. Setting the initial slice to the middle. To display the middle slice by default for each view, axial, sagittal, and coronal, calculate the middle index. Once you have the total number of slices, you can calculate the middle index by dividing the total number of slices by 2. Update initial indices. Set the initial value of current axial index, current sagittal index, and current coronal index to the calculated middle index rather than a hard-coded value like 50. Implementation concept. Here's how the flow should work. Step 1. Fetch slice count. When the application loads, make an API call to fetch the total number of slices for each orientation. Step 2. Set initial indices. Calculate and set the initial slice indices to the middle of the total slice count for each orientation. Step 3. Cycle through slices. Modify the slice navigation logic to use the actual number of slices instead of a fixed number like 100. Practical considerations. Backend support. Your server-side code needs to support an endpoint that provides the total number of slices available for each orientation. This could involve scanning the directories containing the images and returning the count. Browser performance. Ensure that the application efficiently handles the potentially large number of slices, especially when dealing with high-resolution medical images. You might need to implement lazy loading or other performance optimizations to ensure smooth navigation. By implementing these changes, you will be able to fully navigate through all the available slices in each direction and start the viewer at the most meaningful position for users.
Okay, we have GitHub Copilot actually generated the whole code. Yes, it's still checking if they are running in production or not. That's kind of important. We currently have 182 lines. And I just copy that. Yeah, 209. That sounds about right. Okay, the thing is not moving. Just asking for nonce. Okay, that's not fun. Stuffed something up, didn't you? Stuffed something up. Okay, can you actually update the JavaScript code and regenerate the code? Hey, we would like the entire thing without any placeholders, so it can be executed with no errors.
Certainly. Below is the updated JavaScript code that programmatically determines the number of slices in each direction, axial, sagittal, and coronal, and sets the initial index to the middle slice. I've assumed that the backend is capable of returning the slice counts via an API endpoint. Updated JavaScript code. JavaScript const is localhost equals window location.hostname equals localhost. Window location hostname equals 127.0.1. Const base
This JavaScript used to work fine, but with the new version, the images are not being fetched correctly. Can you look at the previous version of the code above and update accordingly? Oh, it's getting stuck somewhere. You're not loading the slices correctly. The volumetric data is loading okay, but the slices are not scrollable, so I can't move through them. Can you look at the previous version of the code and update so I do not get the errors in the image attached? Here is the previous version of the code for your reference.
Welcome to Bionichaos.com, your gateway to the wild world of biomedical data. Our platform is all about making complex data analysis fun and accessible. Whether you're into crunching numbers, exploring neural networks, or diving into fuzzy logic, Bionichaos has got the tools and dashboards to make it happen. We're always evolving, and we want your feedback. Explore our site, try out the tools, and let us know what you think. Your ideas could help shape the future of biomedical data analysis. So jump in, explore Bionichaos.com, and leave us a comment. We'd love to hear from you.
Yeah, there seemed to be a problem in the last response. It didn't finish the code. Can you first just describe in plain language what changes were made to the script, and then we generate the entire code in the next prompt response? Can you do that?
Certainly. Here's a summary of the changes made to the script. Summary of changes. 1. Dynamic slice count initialization. The code now dynamically fetches the number of slices available for each orientation, axial, sagittal, coronal, from the server. This ensures that the indices used to fetch the slices are within valid bounds and that all available slices are accessible. 2. Proper initialization of slice indices. The initial slice indices, current axial index, current sagittal index, current coronal index, are set to the middle slice based on the total number of slices available in each orientation. This replaces the previous hard-coded value of 50. Mubber 3, enhanced error handling. Added error handling to ensure that slice indices are valid before attempting to fetch an image. If an invalid index, e.g. nan, is detected, the code logs an error instead of trying to load a non-existent slice. Improved error logging for scenarios where fetching the slice counts or images fails, making it easier to debug issues. 4. Loading initial slices. The code now ensures that the initial slices are loaded after the slice counts have been fetched. This ensures that the correct slices are displayed when the page first loads. 5. Default fallback for slice counts. In case the server doesn't return a valid slice count, the code falls back to a default of 100 slices, ensuring the application still functions even if the slice count data is unavailable. These changes aim to improve the robustness of the application, ensuring that slices load correctly and that the user can smoothly navigate through all available slices without encountering errors.
Yeah, we obviously had to change the Python code as well. It just pop. Let's talk less. And just send this image, and the Python code, I suspect it needs to be updated.
Your Flask backend code is generally set up correctly to serve the slices and volumetric data. However, there are a few issues and enhancements needed based on the errors and the request structure shown in your screenshot. Issues identified. 1. CSS file not found. The error indicates that styles.css is not found. Ensure that this file exists in the correct path and that the path in your index.html is correctly pointing to it. 2. Missing logo image. The logo image at Bionichaos images/logo.png is not found. Make sure the file exists at the specified location or adjust the path in index.html. 3. Slice counts endpoint missing. The /slice counts endpoint is missing, which is causing the JavaScript to fail when trying to fetch slice counts. 4. Volumetric data not found. The volumetric data file is not being found at the expected location. Ensure that the file exists at static data/volumetric/volumetric.json. Enhancing the Flask code. 1. Add the /slice counts endpoint. This endpoint will calculate the number of slices available in each orientation folder, axial, sagittal, coronal, and return the counts as a JSON response. 2. Ensure static files, CSS images, are correctly served. Verify the existence of the CSS and image files. Also, confirm that they are correctly referenced in your index.html. Updated Flask code. Python import OS from Flask. Import Flask. Send file JSONify. Render template app equals Flask and namecore at app.route. Def in.
It's actually working now. That's much. It's actually working now. It's much better. Yeah, we forgot to update the Python code as well. There is another problem is that the loading times are very high. Maybe in text alone, without any code, before generating the actual code, explain how we can address the high memory usage and the slow loading time of the application. Also, can you explain why sometimes when I load all the slices, it will stop sending GET requests, but then after 5 or 10 seconds it will start talking to the server again. So in other words, I can scroll through the whole, say, axial slices, 250 of them, and they seem to stay in memory. Then when I continue scrolling, there is no GET requests sent to the server. But if I wait about 5 to 10 seconds, it starts sending the same requests again. So why is this happening? Is it a problem at all or not?
Bionichaos.com is a dynamic platform focused on innovative biomedical data analysis. It offers a variety of interactive tools and simulations for EEG, ECG, and other biomedical data types. The site covers topics like neural networks, fuzzy logic, and data visualization, making complex biomedical concepts accessible. Users can explore detailed dashboards, participate in educational games, and even contribute feedback to shape future developments. Visit bionichaos.com, bionichaos.com to explore the tools and leave your comments. Addressing high memory usage and slow loading time. No. 1. Preloading and lazy loading. Problem. Preloading all slices at once consumes a significant amount of memory and can lead to slow loading times, especially with large datasets. Solution. Implement lazy loading instead of preloading all the slices at once. This means that you only load the slices when they are about to be viewed. For example, you load the current slice and a few slices ahead or behind based on the user's scroll direction. This reduces the initial memory footprint and speeds up the initial load time. 2. Memory management. Problem. When all slices are loaded into memory, it can lead to high memory usage, potentially causing the browser to slow down or even crash. Solution. Use object disposal techniques to remove slices from memory when they are no longer needed. For instance, after a certain number of slices have been scrolled past, the images for those slices can be removed from memory. This ensures that only the most relevant slices are kept in memory. 3. Caching strategy. Problem. If slices are repeatedly requested and reloaded, it can cause delays and unnecessary server requests. Solution. Implement a cache strategy where recently accessed slices are temporarily stored in memory, or the browser cache, for quick access. This can be combined with the lazy loading approach. After a certain period or once the memory limit is reached, the cache can be cleared to free up resources. 4. Compression. Problem. Large image files take longer to load and consume more memory. Solution. Compress the images using efficient formats like WebP, which offer better compression rates while maintaining quality. Serving compressed slices reduces both the file size and the loading time. Explanation of the intermittent pauses in GET requests. 1. Browser throttling. Explanation. Modern browsers implement request throttling to avoid overwhelming the server or the client's resources. If many requests are sent in a short period, such as when rapidly scrolling through slices, the browser might temporarily pause sending requests to manage resource usage. Impact. This could explain why, after scrolling through a large number of slices, the requests pause for a few seconds before resuming. This behavior isn't necessarily problematic, but it can be addressed by optimizing how and when requests are made. 2. Garbage collection. Explanation. The browser's garbage collector may kick in to free up memory, which could momentarily halt operations. During this time, the browser might stop sending requests as it reclaims memory, particularly if many slices are being held in memory. Impact. This behavior is typical of how browsers manage memory. However, optimizing memory usage by implementing lazy loading and proper disposal of unused objects can reduce the frequency of such pauses. 3. Server or network latency. Explanation. Network latency or server load can also cause delays in processing requests. If the server is under heavy load or there are network issues, requests might take longer to process, leading to visible pauses in the application. Impact. While this is more of an infrastructure issue, optimizing server response times and reducing the number of simultaneous requests can help alleviate it. Is this problematic? Throttling and pauses in sending requests are not necessarily problematic if the user experience remains smooth. However, if these delays significantly impact usability, it's worth addressing them through the techniques mentioned above, particularly lazy loading, memory management, and caching. These approaches not only improve performance, but also help prevent the browser from being overwhelmed by too many requests or excessive memory usage. To address the high memory usage and slow loading times, a key strategy is to implement lazy loading. Instead of loading all the slices at once, lazy loading allows the application to load only the slices that are about to be viewed. This reduces the initial load time by focusing on loading data just in time based on user interaction. For example, when a user scrolls through the axial slices, only the current slice and perhaps the next few slices are loaded. This method significantly reduces the amount of data held in memory at any given time, making the application more responsive and less resource intensive. Another important technique is memory management. When dealing with large data sets, like the 250 slices in your axial view, keeping all slices in memory can overwhelm the browser's resources. A more efficient approach is to release or dispose of slices from memory once they are no longer needed. This can be done by removing images from memory after they have been scrolled past and are unlikely to be revisited soon. By keeping only the most relevant slices in memory, you maintain a balance between performance and resource usage. Caching strategies also play a crucial role in optimizing performance. Instead of constantly fetching slices from the server, recently accessed slices can be temporarily stored in a cache. This way, if the user scrolls back to a previously viewed slice, the application can quickly retrieve it from the cache rather than sending another request to the server. However, it's important to manage this cache carefully. If too many slices are cached, it can lead to excessive memory usage, so setting limits on cache size and implementing a strategy to clear older or less frequently accessed data is essential. Image compression is another effective way to reduce both loading times and memory usage. By serving compressed images such as those in the WebP format, you can maintain visual quality while significantly reducing file sizes. Smaller files not only load faster, but also consume less memory once they're in use, contributing to overall better performance. The pauses you observed, where the application temporarily stops sending GET requests after scrolling through many slices, are often a result of browser throttling or garbage collection. Modern browsers are designed to manage resources efficiently, and they may pause requests to prevent overwhelming the client or server. This is usually not a problem, as it helps maintain the stability of the application. But if these pauses are too frequent or lengthy, it might indicate a need for further optimization. Garbage collection can also cause brief delays as the browser reclaims memory that is no longer in use. This process is a normal part of how browsers manage memory, but can be minimized with better memory management practices, such as disposing of unnecessary data promptly. Lastly, server or network latency could be contributing to these pauses. If the server takes too long to respond to requests, or if there are delays in network transmission, this could result in intermittent halts in data loading. While this is less about the application code and more about infrastructure, optimizing server performance using a content delivery network, CDN, and reducing the number of simultaneous requests can help mitigate these issues. In summary, the combination of lazy loading, efficient memory management, smart caching strategies, and image compression can significantly enhance the performance of your application. Understanding the root causes of the observed behavior, such as browser throttling and garbage collection, also helps in determining whether these pauses are acceptable within the context of your application's performance goals. By implementing these strategies, you can ensure a smoother, faster, and more resource-efficient user experience. The data from your site's analytics over the past 30 days provides valuable insights into the performance and user interaction with your web application. Let's break down each metric and discuss what it might mean for your application and where improvements could be made. Unique visitors, 5.73K. This indicates that over the past 30 days, 5,730 unique individuals have accessed your site. This is a healthy amount of traffic, suggesting that your application has a decent user base or is gaining traction. Maintaining or increasing this number should be a goal, which might involve optimizing the user experience to ensure these visitors return. Total requests, 125.32K. This number reflects the total amount of HTTP requests made to your server, including those for images, scripts, style sheets, and data files. Given the nature of your application, which likely involves loading many slices of MRI data and volumetric information, this high number of requests is expected. However, this also highlights the importance of optimizing how these requests are handled. Too many requests can slow down the user experience, especially if they aren't efficiently managed or cached. Percent cached, 25.87%. Only about a quarter of your requests are being served from cache, which is relatively low. This suggests that a significant portion of your traffic is making repeat requests for the same resources, which could be unnecessarily increasing load times and server strain. Increasing the cache hit rate should be a priority. You could achieve this by refining your caching strategy, possibly by extending cache durations for static assets like images, CSS, and JavaScript files. Additionally, consider using more aggressive caching for slices that are frequently accessed. Total data served, 4 gigabytes. Over the past month, 4 gigabytes of data has been served to your users. Given the type of content your site is handling, e.g. medical imaging data, this number is not surprising. However, this metric also underscores the importance of data compression and efficient loading strategies to ensure that your site can serve this amount of data without bogging down the user experience. This total could be reduced by implementing more efficient data formats, better caching, and optimized image delivery. Data cached, 1 gigabytes. Of the total data served, only 1 gigabyte was served from cache. While this helps to reduce server load and improve load times for users, the ratio of cache to total data served, 1 gigabyte cached out of 4 gigabytes total, suggests that there is room for improvement. Increasing the amount of data served from cache would not only lower server strain, but also enhance the responsiveness of your application, particularly for repeat visitors. Recommendations. 1. Improve caching strategy. Aim to increase the percent cached by ensuring that more static resources, including commonly accessed slices, are served from the cache. Review your cache control headers and consider increasing the cache duration for files that don't change frequently. 2. Optimize data delivery. Consider implementing data compression, such as gzip or brotli, for files served by your server. This will reduce the total data that needs to be transferred, speeding up load times. 3. Review request handling. With over 125,000 requests, it's important to ensure that these requests are necessary and that they're being handled as efficiently as possible. Implementing lazy loading and intelligent resource management could reduce the total number of requests and improve performance. 4. Monitor and adjust. Continue to monitor these metrics as you implement changes. The goal should be to see an increase in the percentage of cached data and a decrease in the total data served, if possible, through optimization techniques. By addressing these areas, you can improve the performance of your web application, leading to a better user experience, lower server costs, and potentially even higher retention and satisfaction among your users. The images you've provided show the browser cache TTL settings in Cloudflare, which determine how long a visitor's browser caches files before checking for updates from the server. Currently, the TTL is set to 5 minutes, meaning that after 5 minutes, the browser will revalidate the cached files with the server. Impact of the current setting, 5 minutes. Frequent revalidation. With a 5-minute TTL, browsers will frequently check with the server to see if there are updated versions of the cached files. While this ensures that users always have the most up-to-date content, it also increases the number of requests made to the server, contributing to higher server load and potentially slower performance due to these repeated checks. Low cache utilization. Given that a significant portion of your data is static, e.g. images, CSS, JS files, having such a short TTL may not fully leverage the benefits of caching, leading to unnecessary data transfers and higher loading times. Benefits of increasing the TTL. Reduced server load. By increasing the TTL to a longer period, such as 2 months, or even longer for static assets, the browser will cache files for a more extended period, reducing the number of requests made to the server. This can significantly lower server load and improve the performance of your site. Improved user experience. With a longer cache duration, users will experience faster load times on subsequent visits, since their browsers can load assets directly from the local cache without needing to check with the server as frequently. Better cache hit rate. A longer TTL will improve your cache hit rate, meaning that more of your traffic will be served from the cache, which is faster and more efficient than fetching resources from the origin server. Considerations. Content update frequency. If your site content changes frequently, e.g. daily updates to critical content, a shorter TTL might be necessary. However, for assets like MRI slices, volumetric data, or style sheets that don't change often, a much longer TTL, such as 1 month, 2 months, or more, is recommended. Use of versioning. Implementing file versioning, e.g. including a version number in the file name, allows you to safely use a long TTL. When an update is needed, you simply change the file name, e.g. stylesv2.css, ensuring that users get the updated version without having to lower the TTL. Suggested action. Increase the TTL. For static assets that don't change often, consider setting the browser cache TTL to 2 months or longer. This change will improve site performance by reducing unnecessary server requests and improving cache utilization. Implement versioning. If not already in place, consider implementing file versioning to ensure users always get the latest content when it's updated, even with a long cache TTL. By optimizing the browser cache TTL settings, you can significantly enhance the performance and efficiency of your web application, providing a smoother experience for your users while reducing the load on your server.
Okay, so we changed the browser cache TTL to like 2 months instead of 2 minutes. Yes, and here when you scroll through the whole thing, you should stop sending requests to the server. How do I actually check? Let's record and do a reload button. Profiling the page. Well, yeah, that's been. And wait a sec. And let's do another recording. This time do Control F5. Yeah, that's just loading page. I'm not touching the slices yet. It takes forever. I'm waiting for the volumetric data to actually load. Yeah, there are a couple of questions. So it meant to be in the study folder. I increased my cache TTL to from 5 minutes to like 2 months. Yeah, there's a lot to caching. There's also what's called cache reserve. Yeah, so it finally loaded. Took about like 100 seconds or so. So about a minute. And then scroll through the slices as well. Stop it. See what we get. It would not be good, that's for sure. Why did it finish? Why did it finish loading the volumetric data? Hey, I don't see it. Why? How do you scroll through this thing? Yeah, I would think this is where the thing got loaded. I don't see it in the image. That's weird. Maybe it's not even able to show it or something. Is that the microtas? Not sure. JavaScript heap. It's currently 400, over 400 megabytes. Can the bot explain this to me? The volumetric data is loading for a very long time. It takes about 100 seconds. So how's this can be addressed, and where is it in the report of the browser? Just continuous text would be good without any code. Yeah, the screenshots don't really work. Yeah, this is the loading of the volumetric data. Yeah, the screenshots don't represent what's actually on the screen. That's not nice.
The prolonged loading time of the volumetric data, as indicated by the 100 seconds it takes to load, is a significant performance issue that can be addressed by optimizing various aspects of your application. The browser report you provided highlights key areas where improvements can be made. Here's a breakdown of the potential causes and solutions. Potential causes of slow volumetric data loading. 1. Large data size. The volumetric data might be large in size, which naturally takes longer to load, process, and render. If the data file is not optimized or compressed, the loading times can be excessively long. 2. Inefficient data processing. Once the data is loaded, it needs to be processed and prepared for rendering in the browser. If the processing is inefficient, such as unoptimized algorithms or handling the entire dataset at once, it can significantly slow down the application. 3. JavaScript heap and memory usage. The report indicates significant JavaScript heap usage and memory allocation. If too much data is being loaded into memory at once, it can overwhelm the browser, leading to long processing times and potential delays. 4. Rendering overhead. Rendering the volumetric data in Three.js or another 3D library can be resource intensive. If the rendering process is not optimized, it could lead to prolonged frame rendering times and an overall sluggish user experience. 5. Network latency. If the volumetric data is being fetched from a remote server, network latency could contribute to the loading delay. Slow network speeds or server response times could exacerbate the issue. Solutions to improve volumetric data loading. 1. Data compression. Compress the volumetric data before serving it to the client. Formats like .gz, zip, or more efficient volumetric data formats can reduce the size of the data being transferred, leading to faster loading times. This can be done server-side before the data is sent to the client. 2. Too lazy loading and data chunking. Instead of loading the entire volumetric dataset at once, implement lazy loading or chunked data loading. Load only the necessary portions of the data required for the initial view and progressively load more data as needed. This reduces the initial load time and spreads out the processing load. 3. Optimize data processing. Review and optimize the JavaScript code that processes the volumetric data. Use efficient data structures and algorithms to minimize processing time. For example, consider using web workers to offload heavy computations from the main thread, keeping the UI responsive. 4. Reduce memory footprint. Manage the memory usage by disposing of unused objects and data as soon as they are no longer needed. This can prevent memory bloat and reduce the overall heap usage, allowing the browser to handle the data more efficiently. 5. Rendering optimization. Optimize the rendering pipeline in Three.js. Simplify the geometry or reduce the level of detail if possible. Use level of detail (LOD) techniques to decrease the rendering load for distant objects or less important parts of the volumetric data. This can help maintain a smoother and faster rendering performance. 6. Server-side improvements. If network latency is an issue, consider improving server-side performance by hosting the volumetric data on a content delivery network, CDN, that is closer to the end users. This reduces the time it takes for the data to reach the client. 7. Prefetching and caching. Utilize prefetching and caching strategies to ensure that critical data is available quickly when needed. For instance, caching the volumetric data locally on the client can allow for faster access on subsequent loads. Browser Performance Report Insights. JavaScript heap in memory. The high memory usage suggests that the volumetric data is consuming a significant amount of resources. Reducing the data size, improving processing efficiency, and better memory management will help address this. Long task durations. The timeline shows prolonged tasks, indicating potential bottlenecks in data processing or rendering. Optimizing these tasks, possibly by breaking them into smaller, more manageable chunks, will help in reducing the overall load time. GPU memory. The significant use of GPU memory indicates that rendering the volumetric data is resource intensive. Reducing the complexity of the rendering process or using more efficient rendering techniques will alleviate this. In conclusion, addressing the slow loading times and optimizing the performance of your volumetric data will involve a combination of data compression, efficient processing, optimized rendering, and better memory management. By implementing these strategies, you can significantly reduce the load times and provide a more responsive and enjoyable user experience.
Yeah, so we'll have to do way more work on this and benchmark it as well, things like that. You can do it for me as well. Check it out yourself. And how it works on your machine. That will be really good to know. We'll keep going with this one and have a session. I'll see you next time. Don't forget to check out the website. There's lots of interesting stuff. And yeah, we'll be benchmarking all of it. So stay tuned. Bye.